Suppose that this is a piece of iron rod with a current flowing through it. The current flowing, say, in this direction. So this is assuming that we have a battery, for example, that is connected to the two ends of the rod. Now when we have this current flowing through the rod, there would be, if there is a magnetic field as well, if there's a magnetic field going through the rod, assuming that there is a uniform magnetic field that goes over all of the rod. Okay, I'll just show one arrow. Then there would be a magnetic force. There would be a magnetic force that acts on the rod. And again, it would act on every part of the rod that is in a magnetic field. So if the whole rod is in a magnetic field, this force would act on each and every part of that rod. And we have also learned that this force is given by the formula F equals to B I L. Where L here, L is the length of the rod. Now, right, I should also mention that in the past few videos, I have been describing this quantity B as a field strength, in the same sense that of an electric field strength that can give a force to an electric charge. So we could think that a magnetic field strength can give a force on, say, the positive pole, or not positive pole, the north or south pole of a magnet. But the proper name for this quantity B, as it is defined in this equation, for example, the proper name for this quantity B is actually, I'll write it down, it's actually magnetic flux density. That's the proper name, and officially the term magnetic field strength refers to a related quantity to B, but not exactly B. So from now on, I shall refer to B by its proper name, the magnetic flux density, and if it helps in understanding, we might still think of it as a number that tells us about how strong the magnetic field is. And in a later video, when I talk about Faraday's law, I shall explain why it has this rather odd name of flux density. Okay, now let me look at this equation, this force, a little bit more in this video. Let's think about what this force is actually acting on. So, okay, I have said that this force acts on each and every part of this rod that has a current and that has a magnetic field. So that seems clear enough. But what I would like to understand is to understand where this force is actually acting in terms of the atoms, in terms of the electrons. Now, in the iron rod, there are many iron atoms. Okay, there are many iron atoms, and if I think about, say, an atom, say an atom of iron, there would be, as with all atoms, there would be a nucleus, and the nucleus would consist of positive charges of protons and neutral particles of neutrons. Okay, and around the atom there would be negative charges of electrons, right? And these electrons will be moving round and around, or in some way, would be around the nucleus of the atom, and these are negative charges, right? And in a piece of iron, for example, in fact in any metal, each atom, in this case each of the iron atom, would have one electron, maybe near the outer part of the atom, that can come free of the atom, that can move away from the atom, right? And that can move around. So let's say the atom is there, an electron there from that atom is free to move around over the whole iron rod, and if there's a circuit, to move around the circuit. And this is a property of electrons in the atoms of metals. So we call this electron that can come off, we call it a free electron. Okay, so each of these atoms will give out, of the iron atom will give out one free electron. So free as in free to move, free, not free as in you don't have to pay money for it. Although I suppose electrons can be free too. Okay, right. So you have this atom, and there are these free electrons, and you have all these positive and negative charges. So what actually happens when you have a current flowing? Right, what happens is this. If you think of an atom, if you think of, say, an atom in the iron, and you think of the negative electrons around it, and what happens when there's a current is that the electrons, the free electrons would move. So if the conventional current is in this direction, then the free electron would move in this direction. I should use a different color. The free electron will move in this direction instead. Okay. But the protons, the positive charges in the protons would not move. So there are positive and negative charges in the iron rod, but it is only some of the negative electrons that actually move when you have a current. So coming back to the question about the force, so which part of where is the force actually acting on? I mean, the rod is made up of these particles of protons, neutrons, and electrons. There are no other matter. I mean, just have empty space in between these particles. So the force must be acting on some of these particles. And since we know that there's a connection between current and force, so the one obvious answer would be that the force must be acting on the particles that are moving. And in this case, it must be the free electrons, since it's the free electrons that move and conduct electricity. So indeed, that's the case. It's the force, the magnetic force, due to the magnetic field, it does not act directly on the protons because the protons are at rest. It only acts on the flowing electrons. So on each and every electron that moves, so if let's say I would have lots of free electrons that can move. So on each and every free electron that moves, there is a small force acting on it. So there would be a small force acting on this electron. There would be a small force acting on that electron. There would be a small force acting on this electron. So lots and lots of forces acting on all the electrons that flow when there is a current. And the total of all of these forces, the total of all the tiny little forces and electrons, will give the resultant force, which is this big F that we calculate with this formula, F equals to BIL. Okay, so that is the, if you like, the microscopic explanation for the force. Now, but wouldn't it be nice? Wouldn't it be nice if we can also have a formula to calculate the force on each electron? Okay, we might imagine that since if you think of each electron as moving with a certain velocity v, okay, so instead of describing the flow as a current, which is lots of charges moving every second, if we are looking at a single particle of electron moving with a velocity v, can we calculate the force on that single electron? And this is the question I'll try to answer over the next few videos. Right, the first answer that I will try to look at is how to calculate the number of particles. Right, is to try to understand what we mean by the force on each electron. So what we mean by the force on each electron is that if we think about say n, if n is the total number of free electrons, then I can think of the force on each free electron. Okay, if I let this be F, that would be then it would be the total force on all the moving electrons, which is given by this formula, divided by the total number of free electrons. So this is the idea. This is what I shall try to calculate over the next video or so.